In space, it's oxygen that the astronauts need. In fact, since humans breathe out carbon dioxide, astronauts are polluting the air in their own spacecraft as they breathe. And the harder they work, the more they pollute their own air. Too much CO2 is toxic for us, so spacecraft have systems that scrub it out. On Earth, plants are natural CO2 scrubbers. They absorb carbon dioxide during photosynthesis, which is how they make their own food using the energy directly from the sun. In space, it's not so simple. On the ISS, carbon dioxide scrubbers chemically remove excess CO2. These scrubbers use lithium hydroxide powder that reacts with the carbon dioxide to remove the CO2. To manage the removal of carbon dioxide and the supply of oxygen, the atmosphere in spacecraft has to be carefully controlled. On the ISS, oxygen is mainly made from water in a process called electrolysis. Water is split into its component molecules, oxygen and hydrogen, using electricity. Additional oxygen is also supplied from storage tanks carried up to the ISS from resupply spacecraft.
Having been given the go for final approach, the Soyuz now has begun its approach to the docking port of the Zarya control module, now just 111 meters.
Another vital ingredient provided by our atmosphere is water, or H2O. Our atmosphere recycles the water from the Earth's oceans, providing us with this life-giving liquid. Water is needed by our bodies 24 hours a day to keep millions of complex chemical reactions working. It carries nutrients to our cells and it carries waste away. It keeps our temperature regulated and it provides vital lubrications for our joints and our digestive tract. The level of water in our bodies has to be very tightly controlled, and it only takes a small change in our water balance to make us ill. We are expelling water from our bodies all the time. Around 50% of it goes out in urine and solid waste. About 47% is lost through our skin as sweat. The more we sweat, the more water we lose. And this is why, when exercising, it's important to drink water. The rest we lose like this. That's water vapor from my lungs. An average healthy person can lose almost 2.5 liters of water a day. And when you drink less than you expel, your body starts to dry out or dehydrate. We need fresh water, but 97% of the water on Earth is salt water in the oceans. 2% is trapped as ice. This leaves only 1% available as fresh water. So, how do we get it? The sun's energy heats up the sea, evaporating a tiny amount of it into pure water vapor. This water vapor cools and condenses, forming clouds. When the clouds are fully saturated, the fresh water falls as rain or snow. We call this process precipitation. Wind blows some of these clouds over the land, and that's how it gets into our rivers and lakes, and eventually back into our bodies as fresh water for us to drink. And so the cycle continues. But things in space are not quite so simple.
À tous de DDO, attention pour le décompte final. Top, allumage Vulcain. Allumage EAP. Décollage.
Most of the water on the ISS has to be ferried up from Earth. Since it costs around €20,000 for every liter of water that is shipped into space, a glass of H2O on the ISS is the most expensive cocktail these astronauts will ever drink. And in space, astronauts still need to brush their teeth.
Water is forming with the tension of the surface, almost a perfect sphere. Here you can see a very perfect sphere.
Crew members are allocated 3 liters of water daily. If you compare that to life on Earth, we use at least 50 liters of water just taking our morning shower. So in space, recycling water is essential. Wastewater, condensation, and even urine is recycled into fresh drinking water.
When we journey to distant planets like Mars, we will not be able to resupply the missions from Earth. These long-duration missions require sophisticated methods for making their own oxygen and water, recycle the waste, and even grow their own food. ESA has a number of research projects underway to develop these technologies, one of which is Project Melissa.
Dr. Christophe Lesseur is leading the research program to develop a self-sustaining ecosystem. Melissa has been conceived as a self-sustaining ecosystem intended as a tool to understand artificial ecosystems and for the development of the technology for long-term manned space missions.
Today, the target for a Mars mission is to be able to recycle roughly 40% of the food. Why 40% of the food? Because if you recycle or produce 40% of the food of the crew, directly you produce 100% of oxygen and 100% of the water that the crew will need.
Christophe and his team are developing a prototype system that will consist of 5 separate but interconnected compartments. In the first 3, waste will be progressively broken down by fermentation processes. In the 4th compartment, algae and plants will be grown to produce food, oxygen and water. The 5th compartment will mimic the living quarters of a spacecraft, where the astronauts will consume and recycle the food, water and oxygen produced from the first 4 compartments, closing the loop of this self-sustaining ecosystem.
There is another criteria which is very important, is the quality of the food you will need to produce. You can fill the requirement in terms of nutrition with wheat only, but you have to consider the acceptance. And if we feed the crew with only wheat, of course we will have probably some difficulties.
The size of Melissa will ultimately depend on the number of astronauts and what they want for dinner. You would need about 10 square meters growing area per person if you want to live on wheat. Far less if you're happy with algae. Once the basic needs of the crew have been met, the next big challenge they face are the complications of weightlessness. Our bodies have evolved to live with the power of Earth's gravitational pull.
Without it, I would experience weightlessness and float around everywhere instead of having to jog. Like me right now, astronauts find the freedom from Earth's gravity exhilarating when in space. But weightlessness also complicates the business of daily life.
Our bodies have evolved to cope with Earth's gravity. Take gravity away and our bodies begin to develop some unique problems.
One of the most visible effects of weightlessness are the puffy faces that astronauts develop in space. On Earth, it is much harder to pump blood up to my head than down to my legs. The heart has to work against gravity. If I keep this up too long, too much blood would flow to my head and not enough to my legs. Quite soon, I would feel pretty awful.
In orbit, astronauts are in a weightless environment. It is just as easy for the heart to pump blood to the head as it is to the legs. And so blood collects in the head and astronauts experience puffy face syndrome, which causes nasal congestion, headaches and other ill effects.
Astronauts' legs also suffer. The legs get less blood and grow thinner.
Our muscles are also affected by weightless conditions. They lose tone and mass, eventually leading to muscular atrophy, the wasting away of muscle. It's use it or lose it, and the same goes for our bones.